If we're off resident, then although there's a non-zero probability, it's small for the cost transition. Okay, so that's the first order term. And then let's evaluate the second order term, which is written right here. Okay. So in second order, we can take out the first order term, okay, and use and basically do the double prime integral. So suppose we've done that. I've taken out one factor of IH bar, okay, and then what's left is this T prime, and then is the first order term in T prime. Okay. So A e to the I. Correct? Okay. So now let me expand this thing. Okay. So when I expand this thing, I'm going to get a lambda factor, right? I'm going to get a lambda, and let me take this whole thing out to the front. So I get minus I delta lambda squared, right? Because there's an H bar lambda in here, which can't look at H bar. Okay, 0 to T prime. And then we have a product form. Okay, so in here, I'm first going to get, A e to the I delta t multiplied by this, right? So that's A squared e to the I delta t prime e to the I delta t prime minus 1. That's the first term. And of course, I'm going to get the adjoint of this, which is this. Right? Okay. And now I'm going to get some cross terms, okay, which is plus. So we have this is expanded into A plus A dagger, right? So the A dagger A thing requires a plus sign. Okay, e to the minus I delta t. Correct? And then the A from here and the A dagger thing requires a minus sign. E to the I delta t prime e to the minus sign. Okay, so this is our four terms. Right? So now let's think about when I evaluate this integral. If I have time dependence, then obviously I'm going to bring down a factor of delta. Factor 1 over delta. This is saying if I integrate an oscillating term, I'm not going to get as much of a value as if I integrate a constant term. Okay. Are there constant terms in here? Yeah, sure. We have A dagger A and AA dagger. These will have constant terms. Whereas everything else either depend on 2 delta or delta. Those all have time variations, and we neglect those terms simply because delta is taken to be large. We're at a large detuning here. Okay. So if I just pick out these things, I'm going to get minus lambda squared over I delta 0 to t prime. Okay. The constant is just the commutator between A dagger and A, right? Correct? Okay. And then I will add something to the order of lambda squared delta squared, right? Which we neglect. Everything else is of this order. Right? Are there any questions so far? Yeah. You look very puzzled. Yeah, because think about it. These terms either have 2 delta dependence or delta dependence, right? Yeah. So when I integrate that time dependence, I'm going to get 1 over delta, right? Yeah. So those terms vary as 1 over delta squared, whereas these terms vary as lambda over delta. Yeah. Okay. So if you think about it, lambda, we want, in our cavity QED problems, we want the coupling constant to be pretty big. So actually the second order term is bigger than the first order term because the first order term was dependent on lambda over delta. Okay, so now we have a much larger numerator, okay, but denominator being the same. So actually this term is even more dominant than the first order term. Okay. So now in our perturbation expansion, we're going to okay. So the first order term is roughly of order this, right? Whereas the second order term is roughly of order this. The second order term contains something that's this order. So let me just keep this and neglect the first order term. Now, what does neglecting the first order term mean physically? Okay. Look at this. What do we have here? We have operators of the form sigma plus a, right? And then operators of the form sigma minus a tangent. So these are the transitions. So what we're doing by neglecting the first order term is we're saying that the field is so off resonant so as not to cause any transitions. Okay? So that's the physical meaning of neglecting this term. Okay? So once we neglect this term, okay, we can derive an effective Hamiltonian. So, after I write this down, let's take a break. Okay. So we have the zeroth order term, which basically reduces to a identity operator. Okay. And then there was the first order term, which we neglected. Then let me write the second order term as such. Okay. Minus I H bar. Okay. H bar lambda squared over delta. And which this thing, the whole thing we will call H bar chi, with the chi as the some parameter now. Okay. And then what's left is a constant, right? This is going to be dependent on t coming from the integration. And then it's just this a dagger and a thing. Okay. So now if you look at that, that roughly looks like the first order term expansion in a Taylor expansion of exponential, right? So roughly speaking, this is for a short time, this is approximately equal to the exponential of 1 over I H bar, right? We have a minus I H bar, so it would be I over H bar. H bar I. So basically, we arrive at an effective Hamiltonian that is equal to the, I want to define it to be the negative of this, so we get the minus I over H bar, the things that we usually get. Right? So the effective Hamiltonian, how do you get a minus I? You just switch the order of this function. Right? H bar chi, A dagger. And then let's work with this Hamiltonian when we come back from the break. Are there any questions? So in the dispersive limit, in the dispersive interaction limit, two things should make sense. Okay, so first of all is why we neglect this first order term. We typically think that things coming from the first order term are going to be in general bigger than the second order term, but that's not the case here. And the reason is that the off-resonant field will not cause transitions. That's which is modeled by the first order term. Okay. So the second order term is completely, these are only, as you will see, this kind of Hamiltonian will preserve the number of photons. So the number of photons is not lost. There's no exchange of quanta between the field and the atom, although they're still interacting. So that's very interesting because now you have something that is dependent on the strength of the field, but never destroys any photons in the field. So we can probe the strength of the field without absorbing any photons. And this is where we are going to do what we're going to do with quantum non-devolution measurements. Okay. And then we can do some other interesting things with like the Schroeder capacity. Okay.
Could you go back to the integral back?
Yeah.
For that one, how did you work it out to be the computation?
Oh, okay, okay. So you have these two terms, these two products, which will give you one as time dependent. So if I take them now, I will get A dagger A minus A dagger, right? Which is
So why do we ignore everything else?
everything else is dependent on time.
Oh, okay. So
And when you integrate those, we can say that time dependent things are not. The direct way to do this is, when we integrated out the first order term, there was a 1 over delta thing. That's because everything depended on time. Over here, you're going to expect another 1 over delta, which gives you 1 over delta squared. That's fine. Okay, so let's take a 5-minute break.